A very good morning to you, dear students. So today I am just compiling a few videos from YouTube to explain the concepts of equations of motion, then equation of motion of a freely falling body, then distance time graph and velocity time graph. So I have put these videos together and I have made explanations easier. So when you watch these videos, you will find that the concept has been explained so clearly. Okay. So after watching these videos, I would like to hear from you whether you have understood the concepts or not, so that I can help you with few more videos, okay, that can explain in Tamil also. Understand? So if you are interested to listen to Tamil videos, you just text me personally. And if you have understood these videos, well and good. If you have not understood the videos, kindly let me know so that I will try to make things simpler for you. Okay. So graphical representation of motion, it's being explained in the first video. Then after that, equations of motion and derivations of equations of motion also are there. And the final video is about equations of motion of a freely falling body. Okay. So thanks for watching, and kindly comment in the comment box after watching the videos for your attendance. Thank you.
Hello everyone, in this video we'll be discussing about the graphical representation of motion in terms of distance time graphs. Now you might have heard of a story about the hare and a tortoise, wherein these two animals were running a race. Now initially the hare started running very quickly, and after some time he looked back at the tortoise and he felt that the tortoise is going to take a long time. So he went under a tree and started taking rest. Meanwhile, the tortoise, being at the same pace, reached the finish line. And on hearing the applause, the hare woke up and he started running the race again. And after some time, he has reached the finish line. But it was too late for him because the tortoise has already completed the race. Now, here in this race, the tortoise was the winner. But what are we going to do with this race? What we are going to do is to analyze the kind of motions made by these two animals, that is the hare and the tortoise. So this is the data of the whole race in a tabular form. The first column of the table gives us the information about the time, that is in terms of minutes. The second column gives us the data about the distance traveled by the tortoise in terms of meters. And the third column gives us the distance covered by the hare in terms of meters at the end of every minute. Now let us try to analyze what has happened throughout the race. Now initially, when the time was 0, that is the race has not started yet, the distance covered by both the tortoise and the hare was the same, that is 0 meters. That indicates that both of them were at the starting point. Now at the end of 1 minute, the tortoise has covered 20 meters, whereas the hare was pretty fast. He has covered 60 meters at the end of first minute. Now at the end of second minute, the tortoise has covered 40 meters, whereas the hare is at the same place, that is, it is at the distance of 60 meters from the starting point. Now at the end of 3 minutes, the distance covered by the tortoise has again increased by 20 meters to 60 meters. And here the hare has travelled the same distance, which means that the hare is not moving from its place and it is at rest. This may indicate that the hare was taking rest under the tree, during which it didn't move at all. Now this has continued until the end of 5 minutes, where the distance covered by the hare was the same, that is 60 meters, after which it has increased to 100 meters since it has started moving, and at the end of 6 minutes. Now going to the tortoise side, we see that the distance covered by the tortoise is uniformly increasing at a rate of 20 meters every minute. and it has reached the finish line, that is at the end of 100 meters, while completing 5 minutes of the time. So this is the whole story of the race. Now this information is available to us in a form of a few columns and a few rows. So it was pretty easier for us to go to each row and each column and study what has happened throughout the race. But what if we have hundreds of rows and hundreds of columns in a table? It is pretty tedious to go through each table, each row and each column to analyze what has happened in that particular instant of time. So in that case, what we do for convenience is that we plot the whole information in a graph and we try to analyze that graph. And this process becomes very easy in comparison to analyzing the whole table in terms of columns and rows. So here what we will be doing is we will be plotting this data in terms of graph. So let us do that. So here I have the data which we had earlier, and I have a Cartesian plane where the x-axis and the y-axis are marked. Now we will be trying to plot these points here and make a graph out of this data. Now we will be taking the time along the x-axis in terms of minutes and the distance along y-axis in terms of meters. Now let us mark the points here, the time as well as the distance covered. Now for the sake of convenience, we will take two colors, that is one for tortoise and one for hare. Let us take blue color for tortoise and red color for hare because it will be easier for us to distinguish later. So now it's time for us to plot the graph. So we'll begin with plotting the points for tortoise. So the first point for tortoise will be 0, 0, which is at the origin. The second point will be 120, 120. So this is the point, that is the second point. The third point will be 240, 240. So this is the third point. So in this way we can plot all these 6 points for tortoise like this. Now on joining all these points, we get the graph for tortoise, the motion of tortoise. Now let us do the same thing for the hare. For hare, the first point will be 0, 0, which is at the origin. The second point will be 160, which is 160, that is this point. The third point will be 260, 260, which is this point. So in the similar manner, let us mark all these points. Now on joining all these points, the graph that we get is of the motion of hare. So here the red colored graph shows the motion of the hare and the blue colored graph shows the motion of the tortoise. So this kind of representation of a data about the motion of an object wherein the distance is taken along y-axis and the time is taken along x-axis is said to be the distance time graph. So this is one out of the various representations, graphical representations of the motion of an object, and this kind of representation is termed as distance time graph, since we have plotted here the distance against the time in this particular plot. Now let us try to analyze this graph here. So first of all, we will be focusing on this portion of the graph, that is this straight line which is parallel to x-axis or the time axis here. Now since it is in red color, we are pretty clear that it is the portion of the graph of hare, and we see that throughout this graph the distance covered is not increasing, that is it is constant. At the end of first minute it was 60 meters, at the end of second minute it was 60 meters, again at the end of 5 minutes even it was 60 meters. So here we conclude that the hare was at rest throughout the time of this graph. So we say that this graph, this kind of distance time graph, which is a straight line and parallel to x-axis, represents the distance time graph of a body which is at rest or the body which is not moving at all. Now this kind of graph, which is a straight line parallel to x-axis, represents a body at rest. So whenever we come across a distance time graph which is a straight line parallel to x-axis, we can easily conclude that the body is at rest. Now let us concentrate on this portion of the curve. So this is in blue color, so we are clear that it is the motion made by tortoise, or the graph portion of the graph of tortoise. Now here we see that at the end of 1 minute the distance was 20 meters, at the end of 2 minutes the distance was 40 meters, and at the end of 3 minutes the distance was 60 meters. So we see that the distance covered by the tortoise is increasing at a uniform rate. That is, for every 1 minute it is covering 20 meters, and this is happening throughout the race, that is up to 100 meters of distance. Now this is the reason why we can say that the pace at which the tortoise was moving is constant, or in other words we can say that the velocity at which the tortoise was moving, or the speed at which the tortoise was moving, was constant throughout the race. Now this graph is not a line which is parallel to x-axis, but it is a straight line that is inclined to x-axis at certain angle. Now here such a distance time graph of a moving body, whenever we come across one, we can conclude that such a body is moving with a uniform velocity. So whenever we come across a graph which is a straight line and is inclined to x-axis at certain angle, we can conclude that the body is moving with a uniform velocity or constant velocity. Now let us concentrate on the whole red graph here. Since we have taken red to be the color for hair, this whole graph shows the motion of the hair, the pattern of motion the hair has made. Now here we know that the distance time graph, which is a straight line inclined to x-axis, shows that the body is moving with a uniform velocity, and the distance time graph, which is a straight line parallel to x-axis, represents the body is at rest. So that we will be using here to figure out what is happening here. Now this portion of the graph is a straight line and is inclined to x-axis. So we conclude that during this portion of the curve, the hair was in motion and it was moving with a constant velocity, and after that it has stopped for a while, that is for about 5 minutes. At the end of 5 minutes it has started moving again with a constant velocity. So throughout the race the velocity of the hair is changing, I mean it keeps on changing. So that is why we say that considering the whole journey of the hair, we can say that it was moving with a non-uniform velocity, that is the velocity which keeps on changing. So this kind of distance time graph, which is not a straight line as a whole, is said to be a distance time graph of a body with non-uniform motion. Not only this, but we can have a body with non-uniform motion, the graph of a body with a non-uniform motion to be like this even. The graph which is not a straight line, the distance time graph which is not a straight line, can be said to be a body moving with a non-uniform motion. So even this graph, that is this distance time graph, can also represent a body with a non-uniform motion. So this was all about the distance time graph, and in this video we have learned how a distance time graph looks like and how to plot it. And again we have looked at different kinds of distance time graphs, that is the distance time graph for a body at rest or at uniform motion, and also at non-uniform motion. So this brings us to the end of this video, and I hope this video was fully understandable to you. Thanks for watching. Hello everyone. In this video we will be discussing about velocity time graph, which is a form of graphical representation of motion of a body, wherein we plot velocity against time in a Cartesian plane. So let's see how do we do it. Let's say we have a Cartesian plane with x-axis and y-axis. We will take time along x-axis and velocity along y-axis. So now let's say we have an information about the velocity of a moving body at some instant of time. Now we will have to plot all this data here in this Cartesian plane. So our first coordinate point will be 10, 40. The second coordinate point for us will be 20, 40 and so on. So on plotting all these points here and joining all of them, we get a straight line which is parallel to x-axis. So we notice here that the velocity of the body is not at all changing throughout. It is 40 meters per second, not even decreasing or increasing throughout the journey. So here the velocity of this body is a uniform velocity, and whenever there is a uniform velocity of the body, we get a velocity time graph which is parallel to x-axis or time axis. Now what about the acceleration of this body? We know that the acceleration is defined as the rate of change of velocity. But here we do not have any change in the velocity throughout. So we can say that there is no acceleration at all. So the acceleration here will be 0. So whenever we see a velocity time graph which is parallel to x-axis, we can conclude two things. That is, the body is moving with a uniform velocity with 0 acceleration. Now let us try to plot this velocity time information on a Cartesian plane. Now our first point will be 0, 0, which is here in the origin. The second point for us will be 10, 5, which is here. The third point will be 20, 10, which is here. Similarly, we plot all the points, and on joining all these points, we get again a straight line, but this line is not parallel to x-axis. It is unparalleled, or it's inclined to x-axis, we can see. So now let us study the velocity of this moving body. We see here that it was 0 when the time was 0 seconds. When the time became 10 seconds, it was 5 meters per second. When the time was 20 seconds, it was 10 meters per second, and so on. So it is increasing by 5 meters per second every 10 seconds. So it is uniformly increasing, or we can say that the body is moving with a velocity which is uniformly increasing velocity. And now let us try to find out what will be the nature of acceleration in this case. Now we said that it is moving with a uniformly increasing velocity, which means a constantly increasing velocity. Now we know that acceleration is the rate of change of velocity. Now here the velocity is uniformly changing, which means that the acceleration is constant in this case. So here the acceleration is constant. So whenever we see a velocity time graph which is a straight line and not parallel to x-axis with a slope which is positive, we say that the body is uniformly moving with a uniformly increasing velocity and its acceleration is constant. Now let us try to infer what this velocity time graph means. Now this velocity time graph is again a straight line, but it has a negative slope. Now this kind of velocity time graph means that there is a body which is moving with a uniformly decreasing velocity, and whenever there is a decrease in velocity, we have negative acceleration or retardation. So here in this case, the acceleration is constant since it is a straight line, but it is negative since the slope of this line is negative, or the slope of this graph is negative. Now let's say we have a velocity time graph which is of this kind. Now we don't see a line which is parallel to x-axis or with a negative or a positive slope. It is all mixed up. So in this case, we can say that the body is moving with non-uniform velocity. And the acceleration is also variable since it is not a straight line throughout. So on seeing a graph like this, we can infer that the body was moving with a non-uniform velocity with a variable acceleration which is not constant. So this was all about velocity time graph and its different kinds. And I hope this video was helpful to you. Thanks for watching.
Tutorial.
Hello everyone. In this video, we'll be discussing how to find acceleration from the velocity time graph of a moving body. So let's say we have the velocity time graph of a body which is moving with a uniformly increasing velocity. And we know it is a straight line inclined to x-axis like this. Now suppose we want to find the acceleration of this body whose velocity time graph is given to us. For that, let us consider 2 points, which is A and B. Now we want to find what is the acceleration of the body that it has made from point A to point B. Now in order to do that, the first step that we will be going through is to find the value of velocity and time at these 2 points. That is, what is the velocity and time at point A and at point B. So in order to do that, we need to draw 2 parallel lines from A and B perpendicular to x-axis first in order to find the value of time taken. Like this. So the perpendicular from A meets the time axis or the x-axis at a point, and the perpendicular from B meets the x-axis at another point. So these 2 points where these 2 lines touch the x-axis give us the value of the time at these 2 points. So let us say that the time at point A be t1 and the time at point B be t2. Now we have to also find the velocity values at these 2 points, that is A and B. Now in order to do that, we will be following a similar procedure, but this time we will be drawing perpendiculars from these 2 points to y-axis like this. Now the points where these 2 perpendicular lines touch the y-axis gives us the value of the velocities at these 2 points. Now let us say we take the velocity at point A be v1 and at point B be v2. So here in this case our acceleration is provided by the formula which is A equals v2 minus v1 divided by t2 minus t1. Now this gives us the value of the slope of this graph essentially. So the value of the slope of the velocity time graph gives us the value of acceleration at that instant. Now we will have to make use of this formula to find out what is the value of acceleration in this case. So let's do that. Now we see that the value of v1 lies in between 10 and 20. So we can write it as 15 meters per second, which is v1 equals 15 meters per second. And here similarly v2 value seems to be 35 meters per second from this point. Similarly the value of t1 is 30 where this line touches the x-axis, and the value of t2 is 70 seconds where the line touches the x-axis. So we have written down all these things here. It's time for substituting all the 4 values into the expression. So the acceleration will be equal to 35 minus 15 divided by 70 minus 30, which yields 20 divided by 40, that is 0.5 meters per second square. we must keep in mind the unit of a physical quantity whenever we do the problems of any chapter. So here the unit of acceleration is meters per second square. So we write the unit beside the magnitude of the physical quantity. So here we have wrote 0.5 meters per second square as the value of acceleration. Now let us say we have a velocity time graph which looks something like this. Now we know that it is a velocity time graph which is parallel to x-axis. Now such a velocity time graph, we already know it represents a body which is moving with a constant velocity or a uniform velocity with zero acceleration. So here, if we want to find the acceleration, we already know that it is 0 from the graph, but in order to verify that, we can try to find out the acceleration here making use of the formula that we have just now discussed. So our formula we already know, which we will be applying here. Now let us take 2 points A and B, and in between these 2 points we will be finding the acceleration. Now in order to find the acceleration, we need to find the velocity and time at A and B. We know that the velocity value is not changing, which is 30 meters per second throughout. So both the values of velocities, that is V1 and V2, will be 30 meters per second. And in order to find the time at those two instants, we draw two perpendicular lines perpendicular to x-axis. And these two lines, let's say they meet at 2 points where we get the time, which is T1 for A and T2 for B. Now, we will be putting the same formula, that is V2 minus V1 divided by T2 minus T1 to find the acceleration. So let's do that. So here we see that the velocity value, that is V1 and V2, both are 30 meters per second, and T2 here is 70 seconds and T1 is 20 seconds here. So on putting all these values, we get the answer as 0 finally. So this verifies whatever we have already learned. That is, this velocity time graph with a graph which is parallel to x-axis represents a body which is moving with uniform velocity and its acceleration is 0, which is verified here clearly. So this was how we could find out acceleration from the velocity time graph, and I hope this video was helpful to you. Thanks for watching. Hello everyone. In this video, we'll be discussing about equations of motion. Now we have learned about a few physical quantities in the previous videos like distance and displacement, time, speed and velocity, and acceleration. We have discussed in detail about all these physical quantities in the previous videos. Now all these physical quantities are related to each other. They are linked to each other in a certain way, or in many ways we can say. Now these relations between these physical quantities are known as equations of motion. Now equations of motion is a set of equations which relate all these physical quantities that we will be learning in this video. Now we will be considering only one kind of motion whenever we are talking about equations of motion in this particular module. That is, an object moving in a straight road with a uniform acceleration. So we will be considering only this kind of motion throughout this module. That is, the object will be moving in a straight road only with a uniform acceleration and nothing other than this. So whenever an object is moving in a straight road with a uniform acceleration, there is no difference between the terms distance and displacement, since the body is already moving in a straight road. And also there is no difference between the terms speed and velocity. So these terms may be interchangeably used in this module at some point of time. That is, distance or displacement can be used interchangeably, and also speed and velocity can also be used interchangeably. So don't get confused. This is just because the object is moving in a straight road with uniform acceleration. Now, let us learn some notations that we will be using in these equations of motion. We will be denoting these physical quantities by some notations or some symbols that we need to bear in mind if we don't want to get confused by seeing the equations of motion. So, distance or displacement is given by the letter S here, and the time is given by the letter T, and the acceleration is similarly denoted as letter A, small a, and the speed or velocity is denoted by U or V. Now, U here denotes the initial velocity of the body, the velocity that it initially had, and V denotes the final velocity of the body. Now, all these symbols we are going to use when we denote these physical quantities in the equations of motion. So, let us see what these equations of motion are. So, our first equation of motion is V equals U plus AT. The second equation of motion is S equals UT plus half AT squared. And the third equation of motion is 2AS equals V squared minus U squared. Now, the first equation of motion is basically a relation between the velocity and time of the body. So, it is otherwise called as velocity-time relation. Similarly, the second equation of motion is basically a relation between the position and time of the body. That is why it is known as position-time relation. And in the same way, this third equation of motion is a relation between position and velocity. So, it is called position-velocity relation. So, these are all these three equations of motion where the notations that we have seen just a few minutes before are used in terms of the physical quantities. Now, in the next few videos, we will be talking about all these three equations of motion in detail, and also we will be deriving each of them from the graphs, and we will be using all these three equations of motion to solve different problems in motion. So, stay tuned and keep watching. Thank you.
Tutorialspoint.com. Simply easy learning.
Hello everyone. In this video, we will be deriving the first equation of motion, which is otherwise called as the velocity-time relation. We have already seen what it is. It is V equals U plus AT, where U is the initial velocity of the body, V is the final velocity of the body, A is the acceleration, and T is the time taken by the body. So here I have a velocity time graph which is a straight line AB. Now this velocity time graph gives us an impression that the body is moving with a uniform acceleration. So our first step towards deriving this relation would be to draw two perpendicular lines from point B, one towards y-axis which touches y-axis at E, and the second one towards x-axis which touches x-axis at point C. We will be drawing one more perpendicular line from point A to BC which touches BC at point D. Now, we know that this velocity time graph has not started from the origin, which is here. It has started at a point somewhere here which is not the origin or which is above the origin in the y-axis. So, this gives us an impression that the body has not started from rest. That means that it has some initial velocity. So, this OA gives us the value of the initial velocity of the body. So, our initial velocity we have taken as U. So, this length we will be taking as U, that is our initial velocity. And since OA will be exactly equal to DC, since they are the two opposite sides of the rectangle OADC, so DC will be also equal to U. So here OA equals to U, which equals initial velocity of the body, and this also equals DC. Now the final velocity of the body is given by this length, that is OE. That is the final velocity of the body. And since OE equals to BC, BC will be also equal to the final velocity, that is V. So OE equals to V, which is the final velocity, which also equals to BC. Now OC gives us the time taken by the body to reach point B. So this we will be taking as T. Now we know that this graph shows that the body is in uniformly accelerated motion. So let the velocity of the body changes at a uniform rate. This means that the body is moving with a uniform acceleration, and we'll be taking that uniform acceleration of the body to be A, let's say. Now from the graph we see that BC equals to BD plus DC. So BD when added to DC gives us the total BC. So here when we want to find BD, we will be taking DC to the other side. So BD will be equal to BC minus DC. Now we know what are the values of BC and DC, which are V and U respectively. So on putting those values, we have BD equals V minus U. Let us take this equation as our equation number 1. We will be using this equation later on in the derivation. So our equation 1 is BD equals V minus U. Now we know how to find acceleration from a velocity time graph. All we do is to find the slope of the graph. So here we need to find the slope of the graph AB if we want to find the acceleration, which is A. So acceleration is given by BC minus DC divided by OC. So here we know OC equals T, and BC minus DC gives us BD. So here acceleration is equal to BD divided by T, and we have already found the value of BD, which is V minus U. So we'll substitute that value here. So our acceleration A becomes V minus U divided by T on using equation 1. So on taking this T to the other side, that is the left hand side, we get AT equals V minus U. Now on interchanging the terms here, we get finally the first equation of motion, which is V equals U plus AT. So here is our first equation of motion that we have derived from a graphical method using this velocity time graph. I hope this derivation was understandable to you. Thanks for watching.
Tutorialspoint.com. Simply easy learning.
Hello everyone. In this video, we'll be deriving our second equation of motion, which is otherwise called as the position-time relation. Now we already know what is the second equation of motion, that is S equals ut plus half at squared, where S is the displacement, u is the initial velocity, t is the time taken, and a is the acceleration of the body. Here I have a velocity time graph AB, which shows that the body is in uniform acceleration. Now in order to derive this relation, we will be drawing a perpendicular from point B on x-axis, which touches x-axis at point C. Now we know that the body has not started from zero velocity, but it had a certain initial velocity which is given by OA. So our initial velocity is given by OA, which is u, and the final velocity of the body is given by the length BC, which we will take as V. So BC will be equal to V, which is the final velocity, and OA equals u, which is the initial velocity of the body. Now OC is given by the time interval in which the body moves from A to B. So OC is given by time t. So OC equals t, which is the time taken. Now let the acceleration of the body A changes at a uniform rate, which is apparent from the graph here. and the displacement covered by the body will be taking it as S, let's say in time t. Now, from the graph, we see that the displacement of the body here is given by the area under the curve AB, or area under the graph AB we can see. So here the displacement is given by the area under the graph AB. So S, which is the displacement, is given by the area of the trapezium OABC. Here OABC is the trapezium, and if we want to find the displacement of the body from A to B, we need to find the whole area under this graph, which is AB. And this area is given by the area of the trapezium OABC. Now, this shaded region, the area of the shaded region gives us the value of the displacement in this case. Now let us draw a perpendicular line from point A which touches BC at point D. This construction has been made to find the area of the whole trapezium. We will be finding the whole area of the trapezium by first finding the area of the triangle and finding the area of the rectangle OADC, and then adding up these two areas. So that's the procedure that we are going to follow to find out the displacement. So let's move ahead. So here S equals the area of the triangle ABD plus the area of the rectangle OADC. Now we know what is the formula for the area of the triangle as well as for the area of the rectangle. The area of the triangle is given by half into base into height. We will be taking AD as the base of the triangle and BD as the height of the triangle. And for area of the rectangle, we already know which is length into breadth. Here the length we will be taking as OC and the breadth is DC of this rectangle OADC. So let's apply that formula here. So S equals half into base into height plus length into breadth. So S equals half into AD, which is the base, into BD, which is the height of the triangle, plus the length of the rectangle, which is OC, into OA, which is the breadth of the rectangle. So this is the whole formula of finding out this whole area of the trapezium OABC. Now, this BD here is given by BC minus DC. When we subtract DC from BC, we get BD. So we will be putting that here. In place of BD, we will be substituting BC minus DC. We know the values of BC and DC, right? So that is the reason why we have made this substitution here. Now, we will be substituting all the values of this. AD, we know that it is equal to OC. AD is exactly equal to OC since it is the opposite side of a rectangle. So it will be exactly equal to OC. So AD is equal to T. And we know BC, which is the final velocity, equals to V. DC, which is the initial velocity, which is equal to the initial velocity OA, that is U, plus OC, we know it is T, and U is equal to OA, which is already given in the figure. So we have put all the values here in this equation. Now, S will be equal to half V minus U into T plus UT. On evaluating this expression, we will be taking this equation as our equation number 1 and we will be using this equation later on in this derivation. Now, from first equation of motion, we know that V equals U plus AT. So, V minus U will be equal to AT. So, let us take this equation as our equation number 2 here. We will be using both the equations now in the process of derivation. So, this is our equation number 1, which is S equals half V minus U into T plus UT, and our equation number 2 was V minus U equals AT. Now, on substituting V minus U from equation 2 to equation 1 in this place, we have S equals half V minus U into T plus UT. Now in this place of v minus u, we will be adding at, which is from equation number 2. So on doing that, we have s equals half at into t plus ut, which gives us s is equals to half at squared plus ut. Now on rearranging the terms, we have s equals ut plus half at squared. And this is our second equation of motion, which we have finally got. So this is how we derive the second equation of motion, that is the position-time relation. I hope this video was helpful to you and as well as understandable. Thanks for watching. Hello everyone. In this video, we will be deriving our third equation of motion, which is otherwise called as position-velocity relation. We already know what is the third equation of motion, that is 2as equals v squared minus u squared, where a is the acceleration of the body, s is the displacement, and v and u are the final and initial velocities of the body respectively. So here I have a velocity time graph which is AB. Now here, in order to derive this expression, we will be finding out the displacement of the body from point A to point B. So for that, we will be drawing one perpendicular from point B towards x-axis, and the point where it touches the x-axis, let it be C. Now, we know that the body has some initial velocity which we have taken as u. So OA will be equal to u, that is the initial velocity, and the final velocity of the body is given by the length BC of the body, which is v, and OC denotes the time taken by the body from point A to reach point B. Now, let the body covers the displacement of s in time t. So in time t, let the body covers a displacement which is denoted by s. Now, the displacement of the body from the graph we can calculate as the area of the trapezium OABC, which is the area under the graph AB. So it is this area. That is, this area of the shaded region gives us the displacement of the body from point A to point B. So this is what we are going to find here. So S, that is the displacement, is given by the area of the trapezium OABC. Now we know that the area of the trapezium formula is half into base 1 plus base 2 into height, where we generally take the base 1 and base 2 as the two parallel sides of the trapezium, and here the two parallel sides are OA and BC respectively. So we will be taking OA as base 1 and BC as base 2, and the height of the trapezium is given by the length OC. So area of the trapezium OABC equals half into base 1, which is OA, plus base BC, which is the base 2, and OC, which we have taken as height of the trapezium. Now here we will be putting all the values in this expression now. So OA, we already know it is u, which is the initial velocity, and BC, we also know that it is the final velocity of the body, and OC is the time taken by the body. So on putting all these values, we have area of OABC equals half u plus v into t. Now this equation, let us take this equation as equation number 1. Now from the first equation of motion, we have v equals u plus at, from where we can find the value of t as v minus u by a. Now let us take this expression as equation number 2. We will be using these two equations to arrive at our third equation of motion. So the first equation that we have taken is s equals u plus v into t divided by 2, and the second equation that we have is t equals v minus u divided by a. Now we will be putting this value of t from equation number 2 in equation number 1 in this place. That is, we'll be replacing this t by this expression over here. So on doing that, we have s equals u plus v into v minus u divided by 2a. On evaluating this, we get s equals v squared minus u squared divided by 2a. We have simply used the formula a plus b into a minus b, which equals a squared minus b squared. So that's the simple formula we have used here. So on interchanging the terms, that is on bringing 2a to this side, we have 2as equals v squared minus u squared, which is the third equation of motion. So this is how we derive the third equation of motion by this graphical method. I hope this derivation was understandable to you. Thanks for watching. Hello everyone. In this video, we are going to look at the equations of motion for the freely falling bodies. So let's get started. Now we have discussed a lot about freely falling bodies, right? We have seen in the previous video that whenever a ball or an object is dropped from a certain height, it falls down. And this is because of the gravitational pull or gravitational force that the earth exerts onto this object. Now we have also seen in the previous video, that was for acceleration due to gravity, that this ball is accelerating towards the earth with a particular acceleration, which we call the acceleration due to gravity g, and whose value we have found out to be 9.8 meter per second square. So this ball has a constant acceleration throughout its motion towards the ground. So since the body is accelerating with a constant acceleration, the motion that the body is undergoing here in this case is said to be uniformly accelerated motion. So we can conclude that a freely falling body or a free fall is equivalent to a motion which is uniformly accelerated motion. Or we can say that a freely falling body is actually undergoing a uniformly accelerated motion in the vertically downward direction or upward direction. Okay. So here we see that this is a uniformly accelerated motion. This was our conclusion. Now we have a set of equations of motion which we have specifically derived for such a kind of motion, which is uniformly accelerated motion. So those three equations, we can make use of those three equations here in this case also, since this is also a uniformly accelerated motion. So the Newton's three equations of motion for a uniformly accelerated motion are valid for a freely falling body. So this makes a problem simple. We don't have to derive separate equations for this kind of motion, but the equations that we already have, we can very well make use of those equations. But there will be some small modifications in the symbols of the quantities, physical quantities that are there in the equation. So let us see what will be the change. The acceleration is denoted by a in those equations, which we will be replacing by g here, since the acceleration is only because of the force of gravity, and that is the acceleration due to gravity, which has a specific value. Another thing that we need to replace is the symbol for displacement, which is s in those expressions. But here we don't have displacement as such. We don't have horizontal displacement as such. We have a vertical distance or vertical displacement here in this case, which is denoted by a certain height. So we'll be taking that vertical displacement as h. So here we will be replacing a by g and s by h in all those three equations of motion. So let us do that. So the first equation of motion that we have is v equals u plus at, where v is the final velocity of the body, u is the initial velocity of the body, a is the acceleration of the body, and t is the time taken by the body. The second equation of motion is this, which is s equals ut plus half at squared, where s is the displacement, u is the initial velocity, t is the time taken, and acceleration and time, which is a and t. The third equation of motion is 2as equals v squared minus u squared. So these are the three equations of motion which about which we have already discussed a lot, and we have solved so many numerical problems based on these equations. Now it's turn for us to convert these equations to make it handy for us when we are dealing with freely falling bodies. So for doing that, we will simply replace S and A by their respective symbols in case of freely falling body. So on doing that, we have the first equation of motion as, we will simply replace A by G in this expression. So we have the first equation of motion for freely falling bodies as V equals U plus GT, since acceleration is G here, which is due to gravity. The second equation of motion becomes H equals ut plus half gt squared, since we have replaced S by H and A by G. The third equation of motion gets converted to 2gh equals v squared minus u squared. So here we have simply replaced A by G and S by H again. So these are the three equations of motion, or this is a set of equations of motion which is good for us to use for freely falling bodies, or these are the equations that we are going to use, or these are the equations that we are going to make use of whenever we are going to solve the numerical problems here in this chapter which are based on freely falling bodies. So this is the set that we require, but we need some more things to know. We need to know some more things if we want to solve the numerical problems in a proper way. So let us see what are those things. The first thing is the sign convention for G, which means that we need to know that in which case the G value is taken to be positive and in which case it's taken to be negative. So let us see how it is, how it varies. Now let's take the downward motion of a body like this. So in this kind of motion, what happens is the direction of velocity is in the downward direction, and the acceleration due to gravity is always in the downward direction, which is this. So in this case, where the velocity of the body or the motion of the body is in the same direction as that of the acceleration due to gravity, we take the acceleration due to gravity to be positive. So G is positive in this case, where V and G are in the same direction. On the other hand, if we consider the upward motion of a body, that is for in the case where we throw a ball upwards. So what happens there? The velocity is in the upward direction, but the G here, which is the acceleration due to gravity, is in the downward direction, which is pointing towards the downward direction. So in this case, since the velocity and the acceleration due to gravity are in opposite directions to each other, we will take the value of G to be minus G. The acceleration we will take it to be minus G in this case, that is in the case of upward motion. So G is taken as positive if it's in the direction of the velocity, that is when the body is falling downwards, and G is taken to be negative if it is in the direction opposite to the velocity, that is when the body is thrown upwards. Now, this is the sign convention that we are going to use in the numerical problems that we will be solving in this chapter. So you can use any sign convention which is meaningful to you, but this is what we are going to use in this chapter. Now, there are some other things which we need to know before going to handle the numerical problems in this chapter. So the first thing is that when a body is dropped from a certain height. Now let's suppose I drop a ball from this height. I drop a ball, simply drop a ball. I am not giving out, or I am not applying any force onto the ball. I am simply leaving it from my hand. So the initial velocity of the ball is 0. So whenever an object falls down from a certain height, at its initial point it has no velocity at all, but it gains its velocity as it goes downwards because of the force of gravity. So here the initial velocity u is 0 whenever a body is dropped from a certain height or a body moves downward. Now in the other case, which is when the body is thrown upwards. Now when I throw a body upwards, I apply a force already. I apply a force for it to move upwards. So when I apply this force, I am also imparting some velocity to the body, which means that the initial velocity of the body will not be 0 when I am throwing it upwards, but it will go on reducing and finally it becomes 0. So its final velocity becomes 0 at the maximum height that it reaches, and then it starts falling down, which regains its velocity, and that will be equivalent to this motion, which is in the downward direction. So these are the two things which we need to keep in mind, that is, when a body is dropped from a certain height, its initial velocity is 0, and when a body is thrown vertically upwards, its final velocity is 0. The third thing, which is a very important thing that we need to know, is that the time taken by a body to rise to the highest point is equal to the time it takes to fall from the same height, which means that when I throw a ball upwards and then it reaches a certain point, the maximum height, and then it falls down backwards to the earth, back to the earth. Now the third point says that the time this ball takes to reach the maximum height from my hand or from the earth is exactly equal to the time it takes starting from the final point or the maximum height to move downwards. So it basically means that the time it takes for the upward motion to reach the maximum height is exactly equal to the time that it takes for the downward motion at the same height, for the same height. That is said by the third point here, which is the time taken by the body to rise to the highest point is exactly equal to the time taken by the body to fall back to the earth. So with this, we have come to the end of this video, and in this video we have learnt about the sign conventions of G and also a few necessities that we need to solve the numerical problems in this chapter. So I hope this video was helpful to you and also meaningful to you. Thanks for watching.
Tutorialspoint.com. Simply easy learning.